So, yeah, welcome back to this second session of today. Presentations about applied collective intelligence. And my name is Ralf Kurvers, research scientist at Max Planck Institute for Human Development. And I'm gonna start off this session. So let me share my screen. Whoops. Okay, so great. So I'm going to talk to you today about a project we're doing with this group of folks on collective intelligence and open-ended medical diagnostics. And I mean, the background for this line of research is that every year, approximately 250,000 people in the US alone, they die from preventable medical errors. And if you zoom in on what kind of errors these are, you actually realize they are often, not always, but often they're diagnostic errors. And by and large, decisions in the medical domain are taken by single decision makers. Of course, sometimes second opinion, but by and large, there are single decision makers calling the shots. So that led us to ask the question: Can collective intelligence reduce, the amount of diagnostic errors? And I'm going to talk today here in this talk about the pooling of independent decisions. Of course, there are multiple ways of harnessing collective intelligence, but that is the one I'm going to focus on here in this talk. If we look at what is the evidence thus far for can we actually reduce diagnostic errors by harnessing collective intelligence, we now know that aggregating independent decisions by and large outperforms average accuracy across a range of different medical domains and choice environments, which in itself is of course not surprising. So this has been shown in several binary choice contexts in the realm of medical diagnostics. Some studies have investigated multiple choice formats, and some studies have also worked with continuous estimation tasks, where you have to estimate a concrete value. And in all these environments, pooling decisions helps to outperform the average. And again, of course, this is not surprising given what we know about statistical aggregations of wisdom of the crowd approaches. And kind of the current work we are doing, we are trying to kind of take a next step here, and we're trying to see what can we do in an environment where it's actually open-ended medical diagnostics. So all of these previous studies, they generally focus on one context, have a very well-defined format of how to answer the diagnosis at hand. But you can imagine that actually for many problems, there is no predefined list of answers. A user or diagnostician can, for example, enter a free text to indicate a diagnosis and may provide one or actually several diagnoses that he or she thinks might be the correct diagnosis. And so the question we are asking here: can we actually harness collective intelligence in this more challenging environment? So it's not just pooling, one or two options to choose from, but actually it can be many things. And to investigate this, we've teamed up with the Human Diagnosis Project, HumanDX, which is a medical crowdsourcing platform. It's basically a global platform where users can diagnose cases. And this platform has several components. Let me walk you through them. So on the one hand, you have case creators. So these are people who actually make medical vignettes or medical cases. And I'll show you an example of that in a minute. And they submit their cases to expert panels. These expert panels are part of HumanDX. They judge whether they think that a given case is actually representative of a certain medical domain that this case is supposed to be in. They can decline a case if they think it's actually not a valid case given the domain, or they can accept it and then they launch it on the platform. And when it's on the platform, that means it becomes accessible to users. So users can then check out these cases and start diagnosing. So if we look at how does a case actually look, so these are case vignettes, and they are actually based on not always, but mostly on real patient data, where there's actually a number of diagnostic tests have been performed on a patient. And also the final diagnosis is known for follow-up research, but that's not presented yet in these vignettes. So the question for the user is really to find out what he or she thinks the correct diagnosis. So here on top, you see some patient information. So there's a 19-year-old male with chest pain, fever, chills, and malaise. Then there's what they call a finding. So that's a certain investigation that has been performed with certain results. And after observing a finding, a diagnostician can enter a differential diagnosis. And that can be either one diagnosis, it can be a list of many different diagnoses. If they start typing, they will get recommendations, but they can also enter free text. And then they can move to the next finding. And here, for example, here on top, you might see there, this is finding 1 of 11. So there are 11 pieces of information, 11 cues, if you like, to try to home in on the correct diagnosis. You might imagine that this is, of course, a much more challenging environment. How to actually how to aggregate here these very multidimensional medical information. So we relied on a set of about 1,500 unique medical cases or vignettes, and each of them was rated by 10 different diagnosticians, users. And these users, they vary in their level of experience. So that can be medical students, interns, residents, all the way up to attending physicians. And these users also might have different levels or different specialty types of specializations. So to give you a concrete example, this is kind of the information that we received. So you have a case vignette with a correct diagnosis. So in this case, the correct diagnosis is obstructive sleep apnea. And then we have from one rater, we have its final diagnosis. So it's not the whole search process, but just what they submitted in the end after looking at all the findings. And for example, this first individual gave 4 different diagnoses that he or she thought was the correct one. Then there's a second individual who gave only 1 diagnosis, and there are many more. And then there's a last one which gave 2 different diagnoses. And if you look here, you can of course already, for example, see that, okay, there's always obstructive sleep apnea selected by somebody, but also obstructive sleep apnea, which is of course the same thing, but there's also sleep apnea here. So you already see the kind of like the challenge that is emerging here, that you can have terms that actually are spelled differently, or sometimes abbreviated, non-abbreviated, which actually hint at the same diagnosis, where sometimes things that semantically look very close might actually be worlds apart in terms of medical, the diagnostic space you're operating in. So that's kind of the challenge that is here at hand. So to try to address this, we used a combination of natural language processing and combining it with a medical ontology. So in the first step, we use some really off-the-shelf natural language processing steps. So for example, identify all the different words in a given diagnosis, remove stop words, make everything plural single or lowercase, identify acronyms. To try to kind of standardize all these diagnostic inputs as much as possible. After that step, we started relying on Snomed clinical terms, which is a very big medical ontology that basically tries to map out the landscape of the medical domain, not only including diagnosis, but actually many more things. But what we mainly relied on is the so-called concept ideas, so Snomed CT ideas. So for example, here you see there's one ID, and that if you look at the description that is tied to that, you will see, okay, there can be myocardial infection, infarction of heart, cardiac infarction, heart attack. And these are all things that by Snomed CT, and probably also by many experts, because this ontology is of course based on experts, are considered exactly the same thing. So you can already see some of the power that we can harness here by actually relying on these ontologies that really kind of puts different labels in actually exactly the same category. So what we try to do is we try to assign each of these the correct diagnosis of a case. So remember, we had over 1,500 cases, all with a correct diagnosis, and all of the diagnoses that were given by the users when diagnosing these cases, we try to map that to a Snomed CT identifier. We use for this the Jacker similarity index, and we put a very conservative threshold here. So we only actually had to consider something a correct match if there was a perfect match in terms of the Jacker similarity index. So doing this procedure that led us to kind of correctly assign the correct diagnosis to a Snomed CT identifier in roughly 82% of all the cases. So for these 82% of the cases, we actually know what the correct diagnosis is in terms of the Snomed CT landscape, which we believe is indeed the correct diagnosis for that case. We received a similar number in figure, like 82%, when looking at how many of the users' diagnoses can we reliably map onto a Snomed CT identifier. And with that information, we now try to actually start aggregating. So here, for example, we have our three users who gave a certain list of diagnoses. We then mapped that to Snomed CT identifier. So for example, here you then see that OSA obstructive sleep apnea and obstructive sleep apnea, they get the same identifier, which in this case also the correct identifier. And then we started aggregating this information using a 1/n rule. So diagnoses that were given first, they received a score of 1. Diagnoses that were given in the second list of the ranking received a score of 1/2, 1/3, 1/4, etc. And then we basically summed the support for each unique diagnosis given by a crowd member. So we aggregated, and then we ranked this collective list and evaluated whether the correct diagnosis was in the top 1, the top 2, or top 3 rank that we received. And we compared this across different group sizes. The kind of results that we get are shown here. So here you see for different group sizes, starting with single diagnosticians and then up to a group size of 9, we see the diagnostic accuracy expressed in whether the correct diagnosis was in the top 1, top 2, or top 3 of the list. And what you can see here is that we actually are quite successful in actually increasing the likelihood that the correct diagnosis floats to the top of the chain when aggregating more opinions of more or diagnoses of multiple individuals. And this was fairly robust across different medical domains. Okay, one next step we haven't taken yet, is to actually now, of course, we now have just aggregated terms, but you can think of that this actually Snomed CT is actually, of course, it's an ontology, it's a landscape where, of course, there are much more relationships between terms that you can start exploiting. So, for example, here F, of course, that might be a certain diagnosis, and of course it has a parent, in this case C, and it has multiple siblings offspring. And of course, one can now actually start using more complex aggregation rules, where you not just aggregate the things that are exactly identical, but maybe things that are quite close in semantic or in diagnostic space, if you like. So to conclude, so we have seen that pooling decisions increase accuracy in medical diagnostics, and we are also able to do that in open-ended medical diagnostics, which we think is quite exciting. I haven't talked about other forms of how to achieve collective intelligence in medical diagnostics, but it's certainly true that other forms, such as discussion groups and teams, are actually not studied so well, and there's lots of scope for that. And yeah, with that, I want to thank you for your attention, and then we have a few minutes left for questions. Okay, so I see a question of Ben Town asking, okay, so increasing group size is all fine and improves accuracy, but of course increases also the costs. But of course, diagnostic errors are also costly. Have you thought about this trade-off? And yeah, I think that's certainly a very good question. That was also referred to yesterday already, where it was shortly discussed that of course expert time is very valuable. I think what is kind of important here is also to say that okay, it's probably not that we want to have every case diagnosed by 9 independent users. But you can, of course, also think maybe how can we find out which cases we actually need more larger crowds than other cases, right? So one of the approaches we're trying is like, can we actually see if we, after first diagnosis by the first individual, can we then actually decide whether we should actually continue our search for a second diagnostician, or can we actually, by some different ways, actually quantify, that individual is actually, pretty likely to be correct. So I think therefore, like trying to tie like how, what is the crowd size and what is in terms of case difficulty, for example, there I think you can really save, like try to allocate your crowd in a smart way. And next to that, of course, you can also think like maybe there are some areas in the world where it's, labor is cheaper, for example. So you could also think maybe you could actually outsource some things to areas where expert time is less expensive, as in some other areas. So I definitely take that point. It's a super important point. So therefore, we have to really carefully think about how to set this up and where we can actually use this. Yeah. That is I don't just see if there are any raised hands. No, then I'll continue in the chat. How did you determine ground truth, correct diagnosis? So that was determined actually by this is actually determined by the case creator, who actually makes that case and actually follows up with that patient, and follows that person over longer time, and by that then actually finds out the correct diagnosis. So that we fairly, so that I think this is actually a fairly good ground truth here. Yeah, let me take one more question, then we move on to the next one. Is there any potential to integrate Delphi methods where experts see predictions of others and refine? I think that's an excellent question, and I'd love to see more of that work coming out, where you actually get feedback of what others think, and then actually you reconsider. And of course, Delphi methods have been employed usually within one domain, but not really in these open-ended environments yet. But it will be super exciting to see. So for the sake of time, and if I don't want to, I'm happy to. I'll answer the people in the chat myself. Thank you very much for the questions. But for the sake of time, I suggest we move on to the second speaker of this slot. So we're going to hear now from Rongi Aji and Kibai Han. So if you please start sharing your screen. Thank you very much.
Thanks. Just a minute. Can you see my screen now?
Yes, we can. Yeah, it's not in presenter mode, but we can see your screen.
Yeah, okay.
Yeah, perfect.
Yeah. Thanks very much for your kind introductions, and good afternoon, everyone. I will talk about our research about stock intuits today, exploring heterogeneous investor sentiment on social media. My name is Rongjiao Ji from University of Milan, and you can call me Ji. And this work is cooperated with Qiwei Han from Nova School of Business and Economics. Oh, I cannot move. Okay. So I'll just follow this outline and let's start from the introduction. So at the beginning of this year in financial market, what happened with meme stocks got a lot of public attentions beyond the crowd of investors. So meme stocks are stocks that have dramatic price increases, mostly caused by the discussions on social media, like on Reddit, Twitter, or TikTok. These stocks rarely have company fundamentals that back the rise in price. So the first prominent example of this meme stock in this year was video game retailer like GameStop. So when the GameStop its price soared, investors actually have quite distinct opinions and attitudes on it. For novice traders, they especially just jumped into this investment market. They are benefited by the easier approach to execute a trade, but they fear of missing out. So they tend to operate without enough market knowledge and thinking. Well, for professional traders in this case, they act more calmly and don't blindly follow the momentum. As literature revealed, expert investors may outperform the entire crowd on social media, possibly because the social media platform contains unreasonable or misleading information posted by non-experts. So it's interesting for us to understand like whether the investors' profiles influence on their trading sentiment. So in the previous years, investor sentiment already got great interest as it is an indicator of investors' noisy trading behaviors, and it's an object to affect the financial markets. It is sourced from various unstructured textual information, especially on social media that we focused. Social media has great user base, as we know, and contains more information and audiences. Also, through social media monitoring and analyzing, like what Bloomberg did, it can be used to understand better the financial market and to improve the information environment for the investors. So the first property of investor sentiment is that it has the predictability to forecast, for example, the trends of indexes and other market products. Nevertheless, researchers also revealed that it cannot predict precisely the stock's returns, and the magnitude of the effect is economically small. So this may improve by considering the second property, sentiment heterogeneity. The sentiment heterogeneity can be observed according to investors' profiles and trading preferences. It has not been accounted for the current practices of sentiment aggregations, although it's an important source of disagreement. So our objectives of this research are first to identify the semantic information of investor sentiment with variations in topic prevalence. The second and the most important is to understand and characterize the heterogeneity of investor sentiment on social media. Here we cooperate with the financial domain knowledge and also explore the interactions between sentiment and a set of financial specific factors. So for the data, it is collected from the platform called Stock Tweets, which is similar to Twitter, while users are mostly investors for financial discussions. This data contains more than 5 million users' posts, ranging from 2010 to 2015. Especially the equities that was discussed was tagged with the ticker symbols, and the most important, the investor sentiment. It is self-labeled by the users, so which can be used as the ground truth sentiment. By looking at this data, we can see the distribution of the tweets with bullish or bearish sentiment across the users' profiles. So this profile mainly includes the trading experience and trading strategies. Also, in order to involve the informations on industrial level, we matched the asset tickers with the industries and select the top 20 industrial combinations to study with. So after introducing our research objectives, so we can move to the methods part. Starting from this text pre-processing of the posted tweets, first we cleaned the content of the tweets and added time information. Then we need to remove the non-meaningful posts from news robots and then aggregate the tweets into the top 20 industrial that we mentioned. With the aggregated tweets, we can apply now the structural topic modeling techniques by first determining the variables and then select a suit number, a suit topic number. Finally, we were able to estimate the document topic proportions and topic word distributions. So in this way, we obtain the identified topics and the most contributed documents. So for the model STM, it is built on the classical topic models such as SDA. Well, it also brings document level metadata into considerations by adding topical prevalence variable for characterizing the documents, and meanwhile adding the topical content variable for characterizing the words. So in our case, we use the investor trading experience, holding strategy, the related industries, tweet sentiment, and the posted timestamp as the prevalence variable. And we also add the investor trading experience for the topical content variable, as it may influence the practical terminologies and expressions by the investors. So for STM, it's actually very important to select the suitable topic number in advance. So briefly speaking, we performed the exhaustive search of the topic numbers by calculating this held out likelihood and considered also the balance of model complexity and topic qualities. So finally, we determined the topic numbers as 26. And here you can see a summary of the topics together with its correlations. So after describing the modeling process, now let's look at the results. So for the trading experience composition across these topics, this plot illustrates that the investors with different experience show large divergence on topics they are interested in. So first, we can observe that the investors with different trading experience focused on different topics, and they tended to use different words in their posts. So for example, we can see here for novice investors, they focus more on the medicine, travel, retail stores, and Ukraine crisis, and tend to mention more specific events in more details. While for professional investors, they comment more on the green tech, Tesla, and electric vehicle and e-commerce. They instead use more about the market technologies and like to talk about the future tendencies of the categories and also the related financial service. Yeah. So here are 3 examples of the identified topics in detail. So for the first topic, FDA drug approval, it is related to the industrial sectors of healthcare and technology. We can see that it is more focused by the novice traders, while the professional post less on this topic. For the second one, the Greek debt crisis, it is involved in finance and ETF sectors. So we find that it attracts long-term traders to post more, although we can see that it is a hot topic with high posts from all the types of investors. And the last example about the topic on Tesla and electric vehicles, the professional traders can be seen significantly more focused on this topic during the time under study, and the market is generally significantly more bullish towards this topic. Yeah. So for conclusion, first, we explored the heterogeneity of investor sentiment from a large-scale user-generated social media posts. And then we provided empirical evidences to demonstrate that online discussions about investment-related events may be shaped by trading preferences of different types of investors with their heterogeneous beliefs. Moreover, we examined the interactions and identified the semantic content of investor sentiment across the factors, so such as the factors of investor types, the profiles, the sentiment, the categories. And finally, we find that the investor trading preferences may lead them to allocate their attention to different assets with heterogeneous sentiment. So thanks for your attention and welcome to any questions. Yeah.
Thank you very much, Yi. I see we have a first question in from Alexander Staub. Alexander, please.
Hello, thanks for the great presentation. Really interesting.
Thank you.
I was wondering, out of interest, how did you define the experience of the traders?
Yeah, like probably I can share again. Sorry. Like here, I give you an example. Sorry. Sorry, can you see my screen?
Not right, but I can't right now. I'm not sure about
No.
the others.
No.
No. So now, is that okay?
Yeah.
Yeah, yeah, that's nice. So here, like for this platform stock tweets, it actually give us the information of the profiles of the investors. So this is related with the one post, and then here is the user's information. And for example, if we go inside, we can see the background of them. So actually, they list like by themselves. Yeah, for example, here, they listed by themselves like the trading experience and trading strategies they normally use. Yeah.
Ah, okay. So you've got a self-defined.
Exactly. Yeah, that's also like the sentiment is kind of our ground truth sentiment. This is also kind of our ground truth experience.
Okay.
Yeah. Okay.
Thank you.
Thank you.
So I see a question in the chat. Let me read it out to you, Yi. So thank you, great talk. Could you describe a bit more how you determine the percentage of the tweets that belong to every topic?
Yeah, that's a great question. Yeah, so here, like first after applying this structural topic modeling, actually we can got the estimate values for this document topical proportions and topic word distributions. So this document topical proportions basically is the estimate values of this theta. So we can see that for each document, it's like a topical DNA for each document. So we know that it has different values towards the different topics. And then we try to allocate those documents that has like the topic proportions more than, for example, 50%. Yeah, so we select out those documents and then make them as a study object so that we can bring up with these distributions. Yeah.
Cool. Let me finish off with one last question myself. I would like to ask, do you know a bit what actually drives Tim's motivation to share certain tweets between novices and experts, for example? Like, I can think of like a zillion reasons why you actually would share a tweet. Either you want to have more information about, a certain potential investment, or you actually maybe do not want to share a tweet because you think this is going big and you don't want others to hear about this. Do you have more information on that side?
Yeah, I think it is like because in nowadays, like it's a new kind of generation of the trading process. So before, like normally we need to go to like the stock brokers and then listen to their opinions. And nowadays with social media, we can give our opinions and then listen to others. No need to be a professional or common people, so that we can actually analyze by ourselves. So I think that like what we described for novice traders, now they don't really bother to ask for professionals' suggestions. They kind of just believe themselves and then go open the app to do the trade. So I guess that's the reason that because it's a new generations of the trading, so they like to just get the information more and more by themselves and then make the decisions by themselves. So this increase the posts of the tweets, yeah, by everyone. Yeah.
Great. Yeah, thank you so much for the very interesting talk in the Q&As. And everyone can continue chatting on this topic with Lee at the LinkedIn link that has been just shared. Okay, then we're going to move on to the next speaker in the session. It's a presentation coming from Laura Jan, Rasmus Renskin, and Jakob Stark-Ostergaard. Please, floor is yours.
Hi, can you see my screen?
Yes, we can.
Excellent. I just have to minimize this. Thank you very much, Ralf. I'm happy to present our paper, Bot Detecting Jury Selection Procedures to Counter Vote Inflation in Social Media. This is joint work with Rasmus Rensvik and Jakob Stark-Ostergaard, and my name is Laura Jan. I'm a PhD fellow at the Center for Information and Bubble Studies at the University of Copenhagen. Yeah, let's get right into it. I'm going to very briefly walk you through the whole paper, and I'm going to start off to give you sort of the message first and give you the nuts and bolts of the paper in a very brief summary using the graphical abstract, and afterwards going to explain in a bit more detail what motivates our paper, what methods we applied, what the results look like, and eventually share some key takeaways in the discussion with you. All right, so basically we have a problem in the world. This is the key motivation for the whole paper. We find that nefarious, that are sort of the bad guys online, that there's attention hacking bots that shape our public opinion. They elevate or suppress topics by up or down voting social media content. That is, they like or they retweet. So all of those actions you can perform online, this is what we consider a vote, basically. Also, they camouflage among human users to a great extent. That is what makes it so difficult to actually detect those nefarious attention hacking bots and remove them because they behave somewhat human-like. They can be of various types, and we have encoded some of them in our model. For example, we can talk about amplifier bots that just amplify a given topic with a lot of power by an external handler behind it, following a hidden agenda. And that sort of distorts the whole quality judgment. So basically, we could end up with, if you consider those like on a news feed, like tweets, somehow suddenly we see maybe fake news receiving an overproportional share of upvotes and retweets. And if we kind of want to consider that like a collective intelligent judgment reflects upon the quality of the content, we oftentimes observe that this is heavily distorted. So the fake news tweet pops up in our news feed way above the high quality legit tweet. So basically, nefarious bots nullify the reliability of online voting judgments on posts' quality. So this is the problem we see in the world. And now what we did is we developed 2 jury selection procedures that identify and discard those agents classified as nefarious in our model. And yeah, this is what our model looks like in a nutshell. We coded up an ABM that generated a lot of data, which we then decomposed into its singular values, applied some clustering algorithms, used logistic regression and regularization, and eventually selected juries according to the classification that came out of it, that then eventually succeed in greatly improving the majority correctness scores. So those 2 jury selection procedures we end up with, they efficiently restore the reliability of online voting judgments. So you could say that the wisdom of crowds gets another chance here as we actually succeed in removing the bad guys. Yeah, so this is what's ahead of you. And now I'm gonna share all of it in a bit more detail. So first of all, again, what motivates our paper is very much that attention hacking bots influence wisdom of crowds to the worst. So They up and downvote posts following a hidden agenda, and at the same time mimic human behavior. That makes detection super difficult. So what we want to do is we want to remove those from the voting jury. And that is to restore the wisdom of crowds in accordance with the Condorcet jury theorem. Existing work is out there. For example, there's a paper by Galeazzi et al. That comes up with a theoretical model to flag those nefarious votes. However, the chi-square solution is exponential in its complexity and makes it practically inapplicable. Then again, since we also would like to use rather unsupervised machine learning techniques in contrast to supervised elements on very sparse data structures, some work exists, but the methods we kind of apply, they have not yet been applied in the digital propaganda realm, but only on, for example, Congress roll call data. So the goal we have come up with is basically to develop accurate and feasible jury selection procedures. Yeah, I mean, in the best case, that minimize both false positive and false negative classification. So we don't want to exclude users from the voting jury that are actually genuine, but they were wrongly classified as nefarious, and vice versa. We would very much like to not have nefarious agents in our jury any longer. But yeah, that is a trade-off. And we really want it to be feasible in contrast to the research that is out there. So our data set, which the algorithm is going to run on, should require little to no pre-processing, few supervised elements, and reasonable complexity. So this is what our approach looks like. You can kind of split it into three big chunks. So first we modeled our agents in an agent-based model. Then the whole classification takes place, and eventually we select the juries upon the classification. And we end up with two jury selection procedures. That is because we differ in the clustering algorithms we apply. Yeah, that is the only difference, if that makes sense. So first of all, in the agent-based model, we basically just code up a lot of agents and a lot of properties and generate a lot of data. And in each round, or each ABM run consists of an independent voting round concerning a given post, a social media post, and whether it's of high or low quality indicated with P1. And on this post, agents vote in a binary fashion. Each voting round is then initiated with the sampling of a state where we sample whether the post has high or low quality. We sample competencies and beliefs about whether a post has that quality. Then, of course, there's genuine agents and nefarious agents. Genuine agents, that is the good, the human users, they vote independently according to their competence-based beliefs that are strictly larger than 50%. So in alliance with the assumptions that the Condorcet jury theory makes. But then we also have the nefarious agents that are perfectly competent at evaluating nefarious properties that are also sampled. So, and we code up a variety of nefarious agents. One of them, for example, is distorters. They seek to create a lot of noise in the vote profile, for example, by on-cue voting against their beliefs about quality. So they push false news or fake news up on the news feed while voting decent news down. And they are triggered by P3, by property. We introduce a lot of noise in the model that somehow makes it for us very difficult to eventually cluster and classify, makes it very hard for us. And eventually we end up with a huge data set that on which we try to select juries from. The main indicator of interest for us is the majority correctness scores. And that is basically just a subset of all the agents we choose that are in a jury. And we just look at how often they are correct in their vote. And yeah, and we would like to have this majority correctness score approach 1. So just to get an idea of what that looks like before we apply our algorithm. So on the x-axis, we have the majority correctness score, and on the y-axis, the other way around, the number of genuine agents in a population. And as you can see, the genuine agents very expectedly behave like the wisdom of crowds suggests. When they increase in number, they approach a perfect majority correctness score. However, the nefarious agents, when we add those to the population of genuine agents, they delay this effect greatly. So yeah, they substantially lower majority correctness. And then our model is, this is a bit of an overwhelming slide, but what we basically do, we decompose our binary vote data into its singular values. We cluster on the first two components. We do that 5 times because we bootstrap the data sets, and then we cluster once using the k-means algorithm and once the Gaussian mixture model. And then we regress on the mean vote per round of agents clustered together, and we regress on the quality of the post, and we assume this is known because agents vote on quality. Eventually, we then end up with a label vector that labels our agents according to whether they're nefarious or genuine, and we pick the best and the worst juries. And we end up with with a lot of, this is, for example, what the scatter plot looks like, what we cluster on when the noise increases. So here the genuine agents are the black ones. It may be easy to spot the non-genuine ones, the nefarious ones, the colorful ones. However, this gets harder, this task. This is the misclassification results, which all look promising, a bit better for the GMM compared to the k-means. And eventually, this is basically the results table. We end up with majority correctness scores that very much restore the wisdom of crowds in all sorts of population we tried. So this is very nice results. When you see dashes here, this just means perfect score. So one last takeaway to share with you, because I know I'm running over time, is that something very interesting has emerged, and that is that nefarious bots, they face a trade-off because they must obviously hide their activity, because otherwise it becomes very easy for us to spot them and to mark them it becomes easy for social media sites. On the other hand, they only really can sway the majority vote if they act in a coordinated manner, and acting in a coordinated manner means dependencies which we can track. So so that maybe is an idea for food for thought, that we could actually work on attention hack resistant social media vote systems, because it means the bots have to hide more often, and that raises the cost for the handlers of those bots, which makes it more unattractive. You can also combine that with online reputation systems that only publicly display a user's vote once it is a trusted user. That was it. So basically what we did, we ended up with accurate classification that is computationally feasible. It uses a lot of unsupervised elements and reduced supervision elements, and it very much only works with very simple binary input data. Thank you very much. I'm looking forward to hearing your questions.
Great, thank you very much, Laura, for a really, really nice talk. Let me see if there are any questions popping up. Not immediately. Let me then start with a question myself. I wanted to ask, so is it true that all like trustworthy news, all trustworthy agents in your system, that they are quite similar in the decisions they make, whereas bots are very dissimilar, both from the genuine users, but also from other bots? Is that a rephrasing of the result?
I think that's a very good question, and very much points towards the ABM and how it's coded up and how all the assumptions that go into that. We do sample quite a bit when it comes to, for example, the competence level of genuine users. So they are not as similar as, they're not perfect users there. quite imperfect, but they are competent. So their competence is larger than 0.5, but there's quite some heterogeneity in it. There maybe even, I mean, when you think about the scatter plot where you see the agents, some nefarious parts are even more diverse or have lower entropy in terms of behavior that is encoded into the model, if that makes sense.
Yeah, I think that makes. I mean, the reason I'm asking is like we had a look in some of our data sets on the medical domains, and we basically compared how much does the decisions of one doctor compare to the decisions of other doctors. And we see that the individuals that are most similar to the whole crowd are the ones that actually are the very highly accurate individuals. And of course, if you have, for example, two individuals that are like 90% accurate, then they at least need to agree in 80% of the time. Whereas if you have two individuals that are only accurate 50% in binary choice, then they have a minimum agreement score of only 25%. So for us, and then we found out that actually these good users, they're actually very similar to other good users, whereas bad users, they're actually dissimilar from everyone else, including other bad users and also good experts. So that was a really good way for us to filter that out. So that might be interesting to have a look at.
Yeah, thank you very much. Yeah, great input.
Any other?
It sounds like the Anna Karenina principle there.
That's how we called it, yes. Yeah. Okay. All right, and I think it's also time to move on to the last session of last speaker of this session. Thank you very much again, Laura, for a really nice talk. And please continue discussions on the LinkedIn link that was just sent. So then to conclude, we're going to hear from Kuldeep Singh, Palvi, Aggarwal, and Cleotilde Gonzalez. Please, the floor is yours.
Thank you, Ralf. Do you see my screen?
Yes, we do. Yeah.
Okay, thanks. Today I'm going to talk about a social dilemma among defenders and cybersecurity.
Sorry, it's not a full screen mode yet. If you want to do that.
Yeah.
Yes, that's great.
Thanks. And my name is Kuldeep Singh. I'm from Carnegie Mellon University, and this work is done with collaboration with Palvi and Gonzalez, and this work is sponsored by Army Research Lab. So as we all know that the cyber attacks are rapidly growing, and as we are advancing in technology, the attack surface is increasing, and a lot of attacks are happening, and they does not only affect the organization economy or services, but they also have a bad impact on the organization reputation, right? And according to Gartner, there are a lot of worldwide security information requirement are increasing, and in around 2022 they forecasted the market will be around $170 billion. So despite of these huge amount of investment in security, sometimes organizations fail to detect a threat in a timely manner, and that can cause harm to the organization in terms of economy, in terms of finance, but also in terms of reputation in the market. And as we know that attackers try to collaborate with each other and share information with each other and try to exploit the organization. So in 2015, US government comes up with the act, which is Cybersecurity Information Sharing Act, and they comes up with the idea of sharing information among defenders. And we know that by exchanging the cyber threat information among defenders, organization can take an advantage of collective knowledge, experience, and capabilities to understand these cyber attacks, and can come up with the quick solutions to counter these cyber attacks. But why do organizations do not share threat information? We see is as a dilemma. So organizations have a dilemma of not sharing information, and the major factor behind it there are some concern behind it, which is like organization have concern about privacy, and they have concern about competition in the market, and they also have concern about reliability of information they receive or they share with each other. But the another major factor is the lack of incentives and the higher risk. So that basically motivate organization not to share the threat information with each other, and and that's why they are not able to take the advantage of these these collaboration and sharing cybersecurity information. So to study the human behavior, to study this dilemma, we come up with a multi-attacker defender game where we try to observe the human behavior and try to test some hypothesis to see that how humans behave in a cybersecurity information sharing scenario games. So as we know that in a standard business dilemma, two-player standard business dilemma, each player have two options, either to share on defect, and the outcome is based on their action. So Raptor and Gemma suggest that this in standard business dilemma, the cooperation level can be influenced by a parameter they called K index, and which is basically the payoff, the payoff of this business dilemma. So they suggest that if we have a payoff like a payoff which have a higher K index value, will influence the behavior of participants in the PD and can come up with a more cooperative game. So by using this K index, we designed our two experimental conditions, and as we know that there is lack of incentives to share information. So we started with this hypothesis that how this cost or how this payoff matrix will how this payoff matrix will uh, influence the behavior of humans in a cybersecurity threat information sharing game. So we use two payoff matrix, which is condition one, where we have higher K index value, and where when the defender the participant share information, then they have higher payoff compared to the other condition where if they share information, both mutual sharing, they have only 20 points, compared in condition when they have 30 points. And if one of them defect and one of them cooperate, the cooperative one get minus 15 points, and the defective one get 35 points. And in condition one, in the first payoff matrix, we have a penalty of not mutual sharing, compared to we have no penalty in mutual sharing when we comes to the second payoff matrix. So we to test our hypothesis, we design a web-based game, and that game is designed and developed with the help of node game architecture, which allows us to multiplayer interaction, simultaneous interaction during the game. So when players in the starting of the game, players we have some parameters which we try to correlate with real world. So first of all, investment in security. So as organization have to invest in their security, so similarly players have to, before starting the game, they have to invest in their security, and they were provided 2000 endowment point, and out of 2000 they can invest any amount of points in their secure network security initially. And based on the investment, we calculated the probability of attack. So after the first step, they go to the second step, where they were attacked or not attacked based on the probability of attack. So if they have invested higher amount of point, they would have a probability of attack very low, and if they have invested a low number of points, a low amount of points, then they have higher probability of attack. And we have this assumption that a player can, or a network can be secure only 95%. There will always be 5% of vulnerability. That's why if even they invested 2000 points, they are not 100% secure. So in the second stage, when they were either they get attacked or not attacked, if they get attacked, they have to bear the attack cost, so which is which is basically a penalty, and the amount of attack cost is subtracted from their remaining points, and then they have to decide they want to share the information with other participant or other defender in the group or not. And if they choose to share the information with other, they have to bear the sharing cost also. So we have considered a sharing cost here, because for sharing information in real world it required resources, as well as there is a privacy concern that this information can be used in a malicious way. So we consider this as a cost of sharing. And when they decide to share information, this is sharing cost is for one player, and if they decide to share with multiple player, they have to it's just multiplied by the number of defenders they want to share the information. And then in the next step, they got the feedback that if they were attacked or not, and how many, like with whom they have shared the information, and from where they received the information. So receiving information is considered as a reward, and because we consider as this received information can be utilized to patch up the security in the real world. So this reward can be used to patch up the security, and that's why the new probability of attack consider this reward, and the new probability of attack increase or decrease based on the sharing cost and the reward they got in the trial. So this experiment was 100 trial long, like repetitive 100 trials, and we employed 309 participants from AMTRC to run this experiment. And these participants were divided into two conditions. In condition one, we have 156 participants forming of 52 groups, and in second condition, where k-index value is 0.4, we have 153 participants forming of 51 groups. And these players were paid a base payment of $3, and they can earn up to $3.5 in the experiment. And there the objective of the goal of this experiment for participant is to earn as many points as they can, and the average time taken in the experiment was 30 minutes. So we analyzed the data, and we see that first of all, we try to see the proportion of sharing. So we calculated proportion of sharing on three level, which is individual, dyad, and group. So at an individual level, we see that in condition one, where k-index value is 0.8, proportion of sharing is comparatively higher and significantly higher to the condition 2, where k-index value is 0.4. And when we see the dyad sharing proportion, which is mutual sharing, so it means like if both the defenders share with each other in a single trial, that is considered as a mutual sharing. And we see that in the dyad also, the sharing proportion for condition 1 with higher k-index value is more compared to the lower k-index value. And then we also see the group level sharing, which means that all of the defenders share information with each other, with all of the other members in the group in that particular trial. Then we also see the same trend here. The higher k-index influence the higher cooperation in the group. Then we try to see that how their sharing actions were. So we see that in the in the condition 1, where we have higher k-index value, influence the sharing behavior. And we can see on the y-axis we have proportion of action, and on the x-axis we have either they share with one player or both players. So the red bar, which is condition 1, represent the sharing in condition 1. And we see that in condition 1, participants share more with both of the other defender in the group compared to the one defender in the group. Whereas in condition 2, sharing with both and the one defender is same amount of time. It's not very significantly different. It's similar to the one player sharing. So we try to find out the overtime behavior of the participants, that how their sharing of how their sharing actions were over the time during the experiment of 100 trials. And we observed that initially participants were started sharing more with both of the other defenders in the group, and over the time they learn, and they try to they try to find out that how with whom they want to share more. And we see that when they started sharing with one participant, they increase the sharing with one over the time compared to the both. So this suggests that initially they tried to collaborate with both of the players or both of the defenders in the game, and after a certain time they over a certain period of time they learned that one of them is more cooperative or more trusted collaborator than the other, and they try to switch their sharing action and sharing proportions. We also looked at the sharing strategies in human data.
Kuldeep, would be great if you could finish it up in 1 or 2 minutes. Would be great. Thank you.
Thanks. So we see the sharing strategies, and we see that if we observe 4 strategies where if they receive information in previous round or not, and then they shared or not. So R represents receiving and NS represent not sharing. Similarly, NR, NS, not receiving, not sharing, receiving, sharing, and not receiving, sharing. So we see that when they received more information in previous round, they share more in the current round. So it shows that they were reciprocal in the game, and they tried to share more when they received from the other participants. So what we observe here is that the cost or the payoff matrix in this game definitely have an impact an effect on their sharing proportion. And we also see the reciprocity in human behavior, and they tend to share more if they receive information in previous round. We also see that they try to find out a trusted partner in the group, and they share more with that compared to the other participant or other defender in the group. So as a next step, we are working on cognitive model to replicate our human data or human actions or human behavior. And we are also working on machine learning model to find out the optimal sharing solutions for the defender games. Thank you. Questions, please.
Great, thank you so much, Kuldeep. Let's take 1 or 2 questions. There's a question from Ben Town. He asks, how much did the Turkers know each other, and was there any priming to expect future interactions?
So they don't know each other, like they were not aware of each other. And yeah, so we are looking into the interaction of these players, like how they can interact based on the information they have available to them, and how they can utilize that information in an effective manner.
Thank you. Yeah, let me finish myself the last question of this session. So it's interesting to see that kind of individuals really kind of they establish one-to-one bonds with cooperative agents. Do you think that this is maybe also one of the big problems then why there's so little sharing? Because usually there's not one other company that that you have these bonds with about sharing. But actually there's a like a multi-dimensional or there are many companies or institutions that face this problem. So it's really, in that sense, your results suggest that it's actually really complicated in a multi-agent game to actually get this off the ground.
Yeah, so yeah, definitely we see that payoff matrix have an impact on the sharing proportion, and maybe if there is a effective or there is an optimum payoff matrix which can influence the sharing, that is also a point where we are trying to make here. And the other thing, like there are other certain parameters which influence the sharing decision, like the competition and the sharing cost or the privacy concerns. So definitely this is a complex problem, and we are trying to find out the different parameter impact on the sharing proportions.
Cool, great. I really love the work. I think kind of when you share information is actually not very well understood. I really love that you take that angle. Okay, we are a little bit pressed for time. So I want to thank all the speakers of this, I think, very exciting session of 4 talks on applied aspects of collective intelligence. Thank you very much. So my apologies to everyone for taking a little longer in this session. I think we're going to continue in 5 minutes in the panel discussion on ecosystems, global economy, and society. So over to you, Rob, now, or?
So, yes, so no, that's perfect. We will skip the breakout rooms and maybe just take 5 minutes break so that everyone can get a coffee or some water. And yeah, we'll see you back here in 5 minutes for the panel discussion. Thank you very much for the very interesting talks in that session.